Welcome to the third video in this series of videos where I look at the solution to the MOKASA joint examinations, March-April session, Physics Paper 1. And in this video, we are going to look at Section B. So in Section B, we start with question 12. This question is in circular motion, an application of circular motion, and it is on gravitation. We are told that the figure in figure 8 shows a planet, Venus, orbiting the Sun in a circular orbit at constant speed. So its speed along this orbit is constant, and the path is circular. We are required to state what provides the centripetal force. Of course, the gravitational pull on Venus by the Sun provides the centripetal force. And the direction of the centripetal force on the planet is, of course, towards the center of the circular path, definitely towards the Sun. So this is the gravitational pull on Venus by the Sun, and it provides the centripetal force. Notice here that I give you a very complete answer. I'm talking about a force applied on an object by another object. It's very important for us to give our answers as complete as possible. And of course, I've indicated the direction of this centripetal force. The direction of the centripetal force is always towards the center of the circular path. Now let's look at part B of the same question. In part B, we are given that a stone is thrown with a horizontal velocity u from the top of the building of height 125 meters so as to hit a target on the ground 75 meters from the base of the building as shown in that figure. So this 75 meters is usually referred to as the range R, and this is the vertical height which the stone falls through. Calculate the time taken for the stone to hit the target. Now this question is on kinematics, and it is in horizontal projection. When we remember the concepts that we have covered in horizontal projection, they are as follows. If we want to calculate this range, or at least the relationship between the range, the horizontal speed with which the stone is thrown, because this is actually the horizontal velocity, which remains constant throughout the motion, we multiply it by the time it takes to fall from this point all the way to this point, it will give us the range. When it comes to the vertical height, which is actually S, will be given by the u vertical times t plus a half a or gt squared. This equation is obtained from the second equation of uniformly accelerated motion, which states that S is equals to ut plus a half at squared. Now the value of u vertical is 0 because this object is thrown with a horizontal speed. Vertically, its speed is 0. So this reduces our equation to be h is equal to a half g t squared. The other idea that is very important to us is if you've got two objects, two stones, one is projected horizontally and the other one is just released, you will find that they will hit the ground at the same time. This one that is released, the moment it just hits the ground, this other one which was projected horizontally will also just hit the ground. That means when this one is released, when it's here, the one which was projected horizontally is here. When this one is at this point, the horizontal one is at that point. So they are at the same height all the time. All the time. So the time that this object takes to hit the ground is the same time that this one also takes to hit the ground. So when it comes to calculate this time, the best equation to use here, depending on what is given, is this equation here, because the h is that vertical height, which is 125 meters. It's given by a half. G, we are going to take the value of 10, and then we have t squared. So here I can divide, I get 5, and I divide both sides by 5, I get 25. So t squared is going to be equal to 25. T will be equal to the square root of 25, and that is what gives us 5 seconds. That is how long the stone takes to fly from this point to this point. And of course, now if we want the horizontal velocity, we can now revert to this equation here, which states that the range, which is 75 meters, is equal to u horizontal times the time of flight, which is 5. And you can see that u horizontal is actually equal to 15 meters per second. And that is how you would solve this type of question. Part C of the same question, we are given that a stone of mass 0.5 kilograms is attached to a string of length 0.5 meters, which will break if the tension exceeds 20 newtons. The stone is whirled in a vertical plane, the axis of rotation being above the ground, as shown. So this one shows that it is a vertical circle. The angular velocity is gradually increased until the string breaks. In what position is the string most likely to break? At this point, we realize that there are 3 points when it comes to vertical circle. There is this point when the stone is at the maximum point here, point A, we can say point A. It can be at this point, which is point B, and it can also be at point C. When it is at point A, one of the forces that is acting on it is its own weight, mg. The other force which is acting on it is the tension in the string, which is Ta. When it is at the side here, the forces acting on it will be its own weight, mg, which is vertically downwards, and then the tension in the string, which is Tb, is horizontal. The angle between this tension and this weight is 90 degrees. So the only force which provides centripetal force is the tension in the string. However, at point A, the tension in the string and the weight provide the centripetal force. When it comes to point C, there is a tension in the string, which is, we can say Tc, which is in that direction. And of course, the weight of the object acts vertically downwards, mg. Remember, the weight of any object is always acting vertically downwards. Look at mg, vertically downwards, vertically downwards, vertically downwards. So, the point where the string has got maximum tension is at point C, because the centripetal force, being a resultant force, is provided by Tc minus mg is equals to mv squared. That is at point C. At point A, Ta plus mg is equals to mv squared. Of course, there is divided by r because this is centripetal force. And this implies that Ta is equal to mv squared divided by r minus mg. We realize that at this point, this implies that Tc is going to be equal to mv squared over r plus mg. The angular velocity is gradually increased until the string breaks. Suppose we assume that at a certain speed, this is the situation. Then you find that at one point I'm subtracting mg, at another point I'm adding mg. So definitely you can see that Tc is greater than Ta. And of course at point B, it's only Tb which provides the centripetal force. Like that. So you can see if I were to arrange these in order of increasing magnitude, I will have Ta as the least tension because I am subtracting mg. Tb, I'm not subtracting anything from mv squared over r, so Tb is greater than Ta. And of course, lastly, we have Tc being the point where the string experiences maximum tension. So at what position is the string most likely to break? At the lowest point of the oscillation here, at the lowest point of the vertical circle. And you get 1 mark for saying that. Or you can just show it on the diagram. At what angular velocity will the string break? So we are told that the string breaks when the tension in it is just equal to 20 newtons. So we are going to use that information here because it breaks at this point, and we'll say that Tc, which is 20 newtons, is equal to mv squared over r. Let's see whether some kind of speed is given. At what angular velocity? We want to calculate. This symbol here is referred to as angular velocity, and the symbol is supposed to be omega, like this. It's not W. So it's just because of the typing error there. It's drawn like this. It's called omega. So 20 is equal to, we can continue to rewrite this, and we are going to say that this one is given by, centripetal acceleration is given by r omega squared, of course, plus mg. So 20 is going to be equal to the mass of the stone, which is 0.5, times the radius of the circular path, which is 0.5 meters, times omega squared. Now I have m r omega squared plus the mass again, which is 0.5 times 10. And of course this one will be 20. It's going to be equal to, this will give me 0.25 omega squared plus 5. This implies that the value of omega squared is going to be equal to, if I take this 5 to the other side, I'm going to get 15. And of course, I must divide by 0.25. 15 divided by 0.25 gives me 60. And therefore, the value of omega is going to be equal to the square root of 60. And this gives me 7.75. .75 radians per second. That's the value of omega. In question 13, we are asked to define the term atmospheric pressure. Simply put, atmospheric pressure is the pressure exerted on the surface of the Earth by the weight of the air column above it. So that's it. Atmospheric pressure is the pressure exerted on the surface of the Earth by the weight of the air column. What we are talking about is this. If this is the surface of the Earth, then above it we've got the atmosphere. This atmosphere is made up of gas particles, all that. Although the density of the gas decreases as you rise, then we can say there is a point where you will come across a vacuum. So you can consider that weight of an air column and then use the equation P is equals to rho H G. You'll be able to calculate the pressure that this atmosphere exerts at a point on the surface of the Earth, just like you calculate pressure in a liquid. In fact, when we derive this equation, we always say that this equation is used to calculate pressure at a point in a fluid, and a gas is an example of a fluid. So let's look at part B. In part B, we are told that the figure 11 below shows a hydraulic lift supporting a load of 150 kilograms. Its cross-sectional area A1 and A2 are 0.02 meters squared and 0.4 meters squared. So this is 0.02 and this one 0.4 meters squared. You can see that this one is a larger cross-sectional area while this one is the smallest one. We are further told that the length of the effort arm, the effort arm is the distance from the turning point all the way to where the effort is applied. This is the effort. That distance is 1 meter, and the length of the plunger from the pivot is 0.4 meters. This one here is 0.4. And then, of course, there is a force F1, which this system here applies vertically downwards on this piston. Then this piston exerts pressure in the liquid, and this pressure is exerted throughout this liquid because it is incompressible. The same pressure is exerted on the larger area, and because this is a much larger area than that one, then this force is multiplied several times, and then that force is used to lift this load. So we are asked to determine the pressure exerted by 150 kg mass on the liquid. So that one is easy. So in order to calculate pressure, you will need force divided by area. And you can see that these details are given here. So the force is actually the weight of this mass here, which is 150 times 10, weight is equals to mg. The mass is 150 kilograms. The value of the gravitational field strength is 10 Newton per kilogram. And that is what is giving us 1,500 newtons. After this kg and this kg cancel out, we are left with newtons. And that is what I have here. Divide by that area, which is 0.4. And this gives us 3,750. 3,750 newtons per meters squared. Now that pressure, of course, is exerted throughout the whole of this liquid. I'm working in reverse because according to this question, what is required is, what we would have been asked to calculate, the force exerted by the larger piston upwards on the load, is already given. The load is already given. So we can work backwards. So we are asked to calculate the pressure exerted by F1 on the smaller piston. And this pressure is the same as the pressure exerted by this larger piston on the water. So that pressure is definitely 3,750 newtons per meter squared. That pressure is supposed to be the same. Now we want to calculate the force F1. For us to do that, we have got to say that the pressure exerted by F1 on this piston is equal to the pressure that is produced by the piston in the liquid. So that pressure is 3,750. And it was produced by exerting F1 on the area of 0.02. And of course, this one implies that our F1 is equal to, so I have that times 0.02, and I get 75 newtons. 75 newtons. And then I'm asked to calculate the force applied by Fe, that is the effort. So you go back here. We have already worked out the pressure here, 3,750 newtons per meter squared. We have worked F1 is 75 newtons. And now we want to take moments about this point. This 75 newtons tends to turn this system. If it acts in this direction, it tends to turn the system anti-clockwise. But then, for us to apply this force, this stiff rod here tends to apply a force on this rod in this direction. And the amount of force it applies is equal to this force, according to Newton's third law. If this rod is applying a force of 75 newtons downwards, and that force is applied on this rod by this plank, then it follows that the force that the same plank applies on this one is of the same magnitude, 75 newtons. So it tends to turn the system clockwise. It's important to understand this situation. Which is the system that we are concerned with? We are concerned with this plank of wood here. Let's ask ourselves, what forces do we have acting on this system? One of them is the effort. The other one is the force exerted by this plank on it upwards. And of course, we've got some other forces here. But since we are going to take a moment about the pivot, we don't need to know the forces which are acting at this point. So it's important to realize the direction of this force. So clockwise moment is due to 75 newtons. Of course, we are taking moments about this point. So 75 newtons, which acts through this line of action here, times 0.4 is equal to the effort, which is Fe, this one here, times how far it is from the pivot, which is 1 meter. And again, notice that all distances are measured from the same point. This one is 0.4 and this one is 1 meter. And you can see that our effort, that is Fe, it will give us 30 newtons. So you can see an application of a force of 30 newtons. This lever system multiplies that force and makes it 75. And then further still, that force is now multiplied by this system until we get a force of 1,500 lifting this load here. So you can see this is a machine. The effort is 30 newtons and the load is 1,500 newtons. This enables us to calculate the next part, where we are required to determine the mechanical advantage of the system. The mechanical advantage of the system is given by load over the effort. We have seen that the load is 1,500 and the effort is just 30 newtons. And this gives us 50. That is the mechanical advantage. Now, the velocity ratio of the machine is going to be equal to the velocity ratio of the lever system times the velocity ratio of the hydraulic system. The velocity ratio of the lever system is equal to effort arm, which is 1 meter, divided by the load arm, which is 0.4, times the area of the larger piston, which is 0.4 meters squared, divided by the area of the smaller piston, which is 0.02, again meters squared. And you can see that actually the units cancel out and they are going to give us just a number. So we have 1 over 0.4 times 0.4 over 0.02, and this again gives us 50. Remember our mechanical advantage, we had worked it out to be 50. Now this is important because when it comes to working out the efficiency of the system, efficiency is given by mechanical advantage divided by velocity ratio times 100. And you can see that since mechanical advantage is 50, velocity ratio is 50, we multiply by 100 and we find that this machine is 100% efficient. And that is how we would work out that question.